Hello everyone, you are welcome to my YouTube channel at GMAT41. In this video, I quickly want to explain the concept of isothermal process as encountered in thermodynamics. Remember, thermodynamics is a branch of chemistry and it is focused on the energy changes that accompanies chemical reaction. We have these laws of thermodynamics, the first law, the second law. We also have the third law called the zeroth law. And now in our thermodynamic processes, we have isothermal process, we have isochoric process, we have adiabatic process, we have isobaric process, we have polytropic process. Now each of these processes are subjected to certain constant condition of a particular quantity. One of them is the isothermal process. And when we talk about isothermal process, we simply refer to the constant temperature process. What does that mean? In isothermal process, temperature as a thermodynamic variable is kept constant. And so in this video, we shall look at the first law application in isothermal process. First law of thermodynamics, we have the general idea that states that energy cannot be created nor destroyed, but changes from one form to another. The mathematical equation guiding the first law of thermodynamics is as shown on the screen. Delta U equal to Q minus W. Delta U is change in internal energy, and then our Q is the heat of the system. We have W as the work done either by the system or on the system. So these three quantities are related by the formula delta U equal to Q minus W. Now, looking at these quantities, U, that is internal energy, Q, which is heat, and W, which is work. I would like to state that the internal energy, U, being a function of the system, is dependent on temperature. That is to say that internal energy is a function of temperature. Whatever happens to temperature affects internal energy. Now, in isothermal process, if temperature is constant, it means that U will also be constant in isothermal process. And let me say this quickly. Instead of using U, sometimes you can make use of the alphabet, capital E, to represent our internal energy. It is still okay. Alright? Now, for a process that is constant with respect to temperature, it means that if I evaluate T2 minus T1, that is simply change in temperature, final temperature minus initial temperature, I am going to get 0. Are you surprised? Okay, let us get to understand the reason. Temperature is constant. It means if the initial temperature of the system, T1, is 50 Kelvin, for example, then you expect that the final temperature, T2, will also be what? 50 Kelvin. And hence, T2 minus T1 will be 50 minus 50, which will give you what? 0. So what does this mean? Temperature is constant in isothermal process. Therefore, change in temperature, which is final temperature minus initial temperature, will be equal to 0. Now, remember that I told you that internal energy is a function of temperature. That simply means that internal energy, U, is also a constant. Therefore, U2 minus U1, which is represented as delta U, change in internal energy, will be equal to 0. Why? If internal energy is constant in isothermal process also, because it depends on temperature. Imagine that I give you the internal energy of the system to be 20 kilojoule. Say that is the initial internal energy. The final internal energy U2 will also be 20 kilojoules since internal energy is constant. And hence, delta U, which is change in internal energy, U2 minus U1, will give you 20 kilojoule minus 20 kilojoule. And that will be equal to what? 0. Alright, friends. Having explained this concept about isothermal process, It is now time we want to quickly look at the application of first law to isothermal process. Remember the equation delta U equal to Q minus W. If you don't want to use U, you can use capital E. Delta E equal to Q minus W. Delta U in isothermal process is equal to 0. Take note of that, pen it down. Delta U, change in internal energy for an isothermal process is equal to what? 0. Now if that is true, the first law of thermodynamics formula, which is delta U equal to Q minus W, will now become 0 equal to Q minus W. And now, if we have 0 equal to Q minus W, how about I move W to the other side of the equation? Then you will see clearly that W is equal to Q. W is equal to what? Q. Now what we want to do is to establish a formula for calculating W, that is work done in an isothermal process. Now, if I am able to obtain the value, the formula for calculating work done in an isothermal process, then it means that we have also gotten the formula for calculating the heat in that isothermal process system. Remember, we have established that W is equal to Q, since delta U is equal to 0. So let us now focus on the equation W equal to Q. W is work done. When a gas does work, the work formula is given as pressure times dV, where dV is a differential coefficient of volume. So we are simply going to have that W is equal to P dV. Now, whenever a quantity is multiplied by a differential coefficient, to get the value of that quantity, you need to integrate. Yeah, that's what the knowledge of calculus gives to us. So if we have W equal to P dV, to obtain the value of that term, we are going to do some form of integration. We will integrate P with respect to V, because the differential coefficient there is the V, telling us integrate P with respect to what? V. P is pressure of the gas. Alright? Now how can we achieve this? Since we are integrating with respect to volume, V, it means that the pressure must be written in terms of volume. The pressure must be written in terms of volume, because what you are going to integrate is the volume. Since the differential coefficient is the V, you are integrating with respect to volume. How do we introduce volume into this formula now? From ideal gas equation, PV is equal to nRT. So simply, P will be equal to nRT divided by what? V. And so this is what I'm going to do. We know that W is equal to P dV. That P, I am going to pull it off. I'll remove the P and then substitute the value in terms of volume, which is nRT over V. So what we have, the work formula will now become W equal to nRT over V dV. We are integrating the volume term, that denominator V. So that nRT will be brought out because I'm going to introduce integration sign. So watch as we do the analysis on the screen. W is going to be integral nRT over V dV. N is the number of moles of the working fluid, the gas you are using there. R is universal gas constant. T is the absolute temperature in this case. And remember, I already established that in isothermal process, temperature T is constant. So this is the idea. N, which is the number of moles, R, which is universal gas constant, and then T. These three quantities are constant. So they are going to come out of the integral sign. So that W will be equal to nRT integral 1 over V dV. And so the problem is as good as solved. We are going to integrate 1 over V with respect to volume, because the differential coefficient is dV, as you can see. So we're going to integrate that 1 over V with respect to V. We shall integrate from initial value V1 to final value of volume V2. So V1, V2 will be the limit of the integral. If you integrate 1 over V, from the knowledge of integration, you are going to get ln V. You can watch my video lesson on integration and you will get more idea on how to handle this integration if you have any challenge on it. Integral 1 over V will give you ln V. Now remember, we are integrating from V1 to V2, initial volume to final volume. So what do we do in this case? In place of the ln V, we shall substitute the upper limit minus, again, we substitute the lower limit. And so the equation becomes W equal to nRT ln V2 minus ln V1. Now ln shares the property of logarithm because ln is actually logarithm to base E, natural log. So we can apply the laws of logarithm to that ln V2 minus V1 minus ln V1. And if you do that, the formula becomes W equal to nRT ln, open bracket, V2 over V1. Because if you are subtracting 2 logs that are in the same base, key part of the logarithm is going to be the first number over the second number, which in this case we have V2 over what? V1. So what have we been able to establish? The isothermal work W is given as nRT ln V2 over V1, where V2 is the final volume of the working fluid of the gas and V1 the initial volume of the gas. Now I want to tell you something. Isothermal process. We said that isothermal means constant temperature process. So temperature is constant in that process. I would like to quickly take your mind back to a law under gas law. That law is Boyle's law. Boyle's law tells us that if temperature is kept constant, pressure will be inversely proportional to volume. If what is kept constant? Temperature. And of course, the amount of the gas used in the experiment if it is also kept constant. The amount in this case is the number of moles. So according to Boyle's law, the number of moles is taken as constant. Temperature is also constant. So my dear friends, isothermal process is just like an extension of Boyle's law. Both of them are constant temperature process. Therefore, we can apply Boyle's law to isothermal process analysis. Now remember, we derived W, the work done in isothermal process, to be nRT ln V2 over V1. Now according to Boyle's law, P1 V1 is equal to P2 V2. Therefore, if you do V2 over V1, we are going to get P1 over P2. Now why did I do this? I would like you to get the formula of work done in isothermal process in terms of pressure as well too. We have already derived it in terms of volume. We had ln V2 over V1. Now applying Boyle's law, take note, V2 over V1 is equal to P1 over P2. And therefore, we can still express isothermal work formula as W equal to nRT ln P1 over P2. We have obtained 2 formulas. These are the formulas used for calculating the work done in an isothermal process system. nRT ln V2 over V1, or if the problem is given in terms of pressure, it's going to be W equal to nRT ln P1 over P2. Finally, I would like to say this. You may wish to use log in this formula instead of ln. You know, ln is log to base E. Now, if you don't want the base to be E, that is natural logarithm. If you want to solve this question using log to base 10, the formula will take this form. Watch the screen as it displays. Isothermal work W equal to 2.303. You must introduce that constant value. 2.303. nRT log V2 over V1. Or in terms of pressure, it is going to be W, which is work, equal to 2.303 nRT log P1 over P2. So this formula can still be used. However, the truth is I prefer using that of lean for solving problem, and I urge you to also use that. But you can still use that of log, okay, without constant 2.303 to get the same value. Remember that in an isothermal process, work is equal to heat, Q. It simply means the four equations established already, each of these formula is still equal to the heat in an isothermal process. So if I give you a question, for example, 2 moles of a gas at a temperature of 50 Kelvin has a volume increased from 5 meter cube to 15 meter cube. Calculate the work done. Also find the heat. If you calculate the work done, you've gotten the heat as well too. So if I assume that the work done is equal to alpha kilojoule, for example, then the heat would also be what? Alpha kilojoule. What is the value of internal energy in an isothermal process? Don't forget, you don't do any calculation on that. The change in internal energy delta U is equal to 0 in this isothermal process. I hope you enjoyed this video lesson and the explanation of isothermal process. Please like and subscribe to my YouTube channel. Like this video, share it to your friends, other scholars, so that you can get access to this quality teaching. And of course, always remember that I appreciate your comment. Leave your comment here. If you have a question, feel free to drop it in the comment section, and I'll just be right there to give a response to that question. Meanwhile, remember I gave a question example while explaining the concept of isothermal process using 2 moles of a gas, temperature at 50 degrees Celsius, or 15 Kelvin rather, initial volume of 5 meter cube, and final volume of 15 meter cube. How about you use that to find the isothermal work and the isothermal heat? Drop your answer in the comment section. Let's see how far you went about it. I'll be seeing you in my next video lesson.